Okay, here's part one of the lecture covering water waves. Water waves are an example of two-dimensional circular waves. That is, the water waves propagate on the surface of water, and they do so in two dimensions. So picture, for example, the board right here as the surface of water, and then imagine a single point source tapping the water like so, and it does so with some defined frequency. This then means that propagating outwards from that point are a series of circular water waves, those circular water waves that are concentric, and they are centered, of course, on the source itself. So let's imagine that the source is coherent, that is, the frequency is constant. So I have a point source with a constant frequency, and that is then tapping the water. And then propagating outwards from that point, let's say right here is the source, are a series of circular water waves like so. Now typically when we draw these circular water waves, what I'm drawing here are the crests of the waves. Those are the portions of the waves that are coming out of the board the greatest, and then in between would be the troughs. For example, let's say that right here is a trough, like so. This would be the portion of the wave that is deepest into the board, like so. Okay, let me go ahead and erase that trough, however, it's just kind of in the way at the moment. Now, if the frequency is a constant, then you have right here the distance from crest to crest, for example, as being equal to the wavelength lambda, and then therefore speed is equal to wavelength multiplied by a frequency. Okay, with respect to the speed of water waves, however, the speeds of water waves is a pretty difficult problem in fluid mechanics. So then therefore, let me just kind of summarize the speed of water waves in the following manner. Okay, now in deep water, the speeds of water waves are dependent upon the square root of the wavelength. So the bigger the wavelength, like with big ocean swells, for example, the bigger the speed, the smaller the wavelength, the smaller the speed. So in the short clip from the Mechanical Universe episode that I've posted for you, they do a very nice job of showing that with some animation. I invite you to pause this film right now and go ahead and take a look at that clip if you haven't already done so. Okay, now if you're talking about shallow water, that is where the wave itself actually interacts with the ocean floor, for example, then the physics changes. The speed of the water wave is dependent upon the square root of the depth. Like so. So this then means that waves slow down, for example, as they approach the shore. When they do, they rear up because some of the kinetic energy is being converted into potential energy. And this also explains why waves break as they encounter the shore. This is also nicely explained in the Mechanical Universe episode clip. Once again, I invite you to take a look at that. But here is basically what is being described in that portion of the clip. Let's say that, for example, right here is a water wave approaching the shore. Let's say that right here, for example, is the ocean bottom, like so. Okay, the top of the wave, well, the water at the top of the wave right here is deeper than it is, for example, at the bottom of the wave. It's shallower at the bottom of the wave. So then therefore the top of the wave moves more quickly than the bottom does. Bottom moves slowly. So then therefore eventually the wave basically folds over and breaks like so for that reason. So that explains why you always see waves break as they encounter the shoreline. Okay, okay, let me do a little bit of erasing here. Okay, getting back to the water waves themselves, as I've already described, they are circular in nature and they're propagating here in two dimensions on the surface of water. Okay, now very quickly the amplitude of these waves goes down, and it's not necessarily due to damping. Instead, the energy associated with the waves is spreading out over an increasingly larger and larger surface area as the waves propagate. So then therefore, for that reason, the amplitude begins to decrease immediately. Okay, now when you go down to the ocean shoreline, for example, and you look at the waves as they propagate towards the shore, you typically don't see circular waves. Instead, you see what are referred to as plane waves. So then therefore, if circular water waves are circular in nature, what is it then therefore that explains plane waves? Well, you can picture the production of a plane wave a couple of different ways. Okay, so for example, let's say right here is the coastline, like so. Let's say that LA is down here somewhere. Then let's say that we have a storm out in northern Pacific Ocean. And by the way, when it comes to ocean waves, most of the time ocean waves are produced entirely by the weather, produced by the wind. Only under extreme circumstances involving seismic events, for example, with the production of tsunami, could you have waves produced by another physical mechanism. But with respect to ordinary ocean swells that you'd see on a typical day, all of that is basically being produced by the wind. So let's say that right here out in the Pacific Ocean somewhere, there's basically a storm, and then waves are propagating outwards from that point like so. Okay, and then as I said, they're circular in nature. However, basically what you're looking at is just a small portion of what is overall an extremely large circular wavefront by the time that it reaches the shoreline like so. So then therefore, if you're looking at only a small portion here of this circular wave crest, then therefore for that reason it basically looks like a straight line, once again referred to as a plane wave. Okay, but there's another way to produce a plane wave on a small scale, and this is going to employ what is referred to as Huygens' principle. Christian Huygens was a Dutch physicist who lived around the same time as Isaac Newton. He was one of the first scientists to quantify basic properties associated with waves. Let me illustrate. Okay, here's how you spell his name. Once again, his name is pronounced as Huygens. Huygens assumes the following with respect to the production of a plane wave. He assumes that arranged into a line, like so, are a series of point sources. These point sources here then produce circular wavelets, as he referred to them as, which then propagate outwards from those points. Now I'm just going to draw these circular wavelets to the right-hand side here in the diagram, but propagating outwards from this point right here is a little circular wavelet like so. Here's another one from the second source, and so on, and so on, and so on, and so on, like so. And then these circular wavelets here, they then encounter one another, and then when they do, they then constructively interfere. When they constructively interfere with each other, that then produces right here a straight line, like so. So right there in black is a plane wave crest, which then propagates in this direction. I demonstrate this, by the way, in one of the film clips that I've uploaded for you. It's called Ripple Tank Demonstrations Part 1. Go ahead and pause this film right here and take a look at that series of demonstrations that I posted for you if you haven't done so already. But once again, you can produce a plane wave here by means of Huygens' principle. We have here a series of point sources, and then propagating outwards from each is a circular wavelet, as Huygens referred to them as, and then those circular wavelets encounter one another and then constructively interfere to produce a plane wave. So the circular wavelets constructively interfere to produce a plane wave. Okay, now I mentioned a few minutes ago, for example, tsunami. Let me give you a brief description as to why tsunami are so destructive. I invite you to also take a look at the YouTube video clip of the horrible tsunami that occurred back in 2007 off the coast of Japan and in Japan. I invite you to take a look at that clip if you haven't already done so. I believe it was 2007. Maybe it was 2011. I forget. I think it was 2011, actually. Okay, let's first of all compare ordinary ocean swells to tsunami. All right, so let's say that right here we have a series of ocean swells, like so, and then right here is the wavelength lambda. And when you're talking about ordinary ocean swells, the wavelength lambda is typically in the neighborhood of a few meters, maybe at most a few tens of meters. Those of you that surf, for example, may be familiar with this a little bit already. When it comes to ordinary ocean swells, the actual faces of the waves themselves can reach a pretty large amplitude, usually at most maybe about 100 feet or so. And the reason why ocean waves typically can't get any bigger than that is because when they reach those heights, they basically start to slump under their own weight. So then therefore, for that reason, typically you're never going to see ocean waves with faces that are greater than about 100 feet or so. This is, for example, what big wave surfers are surfing when they surf these really big waves. At any rate, however, when you look at those waves, then as they propagate towards the shore and eventually break onto the shore, they're obviously very impressive. However, they don't do much damage. They may destroy some docks or some boats that are right there on the shoreline, but they don't completely inundate the shore like tsunami do. What's the difference between ordinary ocean swells and tsunami? Once again, tsunami are typically produced by seismic events, like, for example, what happened off the coast of Japan back in 2011. The reason why tsunami are so destructive is because the wavelength is huge. A typical tsunami wave doesn't look like this. Instead, it looks like this. Basically, like so, with an enormous wavelength. It's essentially like a huge cube of water, if you will, that has been more or less lifted up and is then propagating towards the shore. Because the wavelength itself is huge associated with tsunami waves, this is why in deep water they travel so quickly. They actually move at speeds that are comparable to the speeds of commercial aircraft, in the neighborhood of maybe 500 to 600 miles per hour. However, as they approach the shore, they then slow down and they rear up as kinetic energy is being converted into potential energy, and then eventually the waves propagate onto the shoreline. But when they do, it's as if an entire portion of the ocean has been lifted up, this more or less cube of water here, and has then been deposited onto the shore. So this is why it's sometimes referred to as a tidal wave, because if you're, unfortunately, standing here and this huge shelf of water is coming at you, it's like an incoming tide. It's an incoming tide that simply does not stop. So I invite you once again to take a look at some of the footage from the Japanese tsunami that occurred back in 2011. It's like something out of a science fiction film. It's absolutely unbelievable when you see that footage, and that's what unfortunately occurred in that event a few years ago off the coast of Japan. Okay, next. Water wave refraction. Let me introduce this topic in the following way. Let's say, for example, that you go down to the beach here in Pacific Palisades. And when you do, the beach here in Pacific Palisades is roughly facing south-southwest. And then you look at the plane waves propagate towards the shore, and then they eventually break onto the shore. When you look at the wave crests themselves, the wave crests, when they break, are parallel to the shoreline. Okay, now, let's say that you go down to Manhattan Beach, which is south of the airport, and when you do, the beach down there, it's almost a 90-degree turn with respect to what we're seeing here in Pacific Palisades. So then therefore, if you go down to Manhattan Beach, for example, you're basically facing due west. And then you look at the water waves as they propagate towards the shore, and you see exactly the same thing as you did, say, here in Pacific Palisades. You see the crests of the plane waves parallel to the shore just prior to breaking. Regardless of which way the beach faces, you always see the same thing. The reason for that has to do with what is referred to as refraction. So let me describe it now in the following manner. Let's say that right here is a boundary between deep water and shallow water. And then as waves propagate from deep to shallow water, they are going to slow down. Okay, let me go ahead and draw a couple of wave crests. So let's say that right here is a wave crest like so, associated with a plane wave. And then here's a second one right here. And then right here, the distance between the two is equal to the wavelength. Okay, the direction of propagation of these waves is perpendicular to the crests. We draw an arrow like so to refer to that direction of propagation. And this is referred to as a ray. Right here is a right angle. Okay, now on this diagram, we define right here a specific angle. This right here is referred to as theta sub I. It's the angle that the individual wave crests make with respect to the boundary. This is called the angle of incidence. Okay, now the speed of the waves here in the deep water, let's just call it v, is equal to the wavelength multiplied by the frequency. But then the waves cross the boundary from deep to shallow water rather, and they slow down when they do. So let's write the new speed as v prime, like so, and the old speed v is greater than v prime. So if the waves slow down, but the frequency of the waves is the same as they cross the boundary, the frequency of the waves, by the way, is governed by whatever it is way back over here that's producing the original plane waves. But if the frequency is the same as the waves cross the boundary, as the waves slow down, this then means that the wavelength has to be smaller. In order for the wavelength to be smaller, this then results in a change in the direction of propagation. That is, when the waves refract across the boundary, now the plane waves look like this, like so. Notice that I've drawn them closer together. Right here is the new wavelength, we'll call it lambda prime, so then therefore the new speed v prime is equal to that new wavelength, but then multiplied by the same frequency. The direction of propagation is once again perpendicular to the refracted wave crests. That looks like this right here. Once again, right here is a right angle. We also define here on this diagram another angle. This is the angle that the refracted wave crests make with respect to the boundary between deep and shallow water. This is called theta sub r, and it's referred to as the angle of refraction. But notice the change in the direction of propagation. So let's say, for example, that down here somewhere is the shoreline, like so, and then out in Santa Monica Bay, let's say that the waves are originally propagating like this, but as they approach the shoreline, they more and more slow down and refract as they do, like so, such that just prior to breaking on the shore, the plane wave crests are then therefore parallel to the shore. So this explains why you always see what you do when you go down to the beach, regardless of which way the beach faces. It always looks the same, basically, for this reason. Okay, now there is a very simple geometrical relationship here that relates this triangle here before the waves refract and this triangle here after the waves refract. Notice that these two right triangles here share the same hypotenuse, like so. So then therefore, because they share the same hypotenuse, I can write a simple trigonometric relationship between the two. Here's then how we go about doing so. Okay, so first of all, take the top triangle here, and I'm going to write down the sine of the incident angle. Okay, the sine of the incident angle is equal to the opposite side of the triangle, which is right here. Notice that's equal to the wavelength lambda, but then divided by the hypotenuse h. Okay, now take a look at the bottom triangle right here, and now I'm going to write down the sine of the refracted angle. Okay, the sine of the refracted angle is equal to the opposite side of that bottom triangle. That's this side right here, which is the wavelength lambda prime, but then divided by the same hypotenuse h. What I'm now going to do is just cross multiply each of these guys and solve for h, and then set them equal to each other. So with the expression on the left here, if you solve for h, you get lambda over sine theta incident, like so. And then over here on the right-hand side, solve for h here, and you get lambda prime over sine theta refracted, like so. Typically with this expression, however, what we do is we don't write the numerator in terms of the wavelengths. Instead, we write them in terms of the speeds. So what I'm going to do is multiply both sides of the expression by the frequency f, like so. And then right here in the numerator on the left-hand side of the expression is the speed of the waves in the deep water v. And then on the right-hand side of the expression, this right here is the speed of the waves in the shallow water, v prime. Like so. And I end up with this relationship right here. This relationship here is given a name. This relationship here is referred to as Snell's Law. As we'll see a little bit later on, Snell's Law is extremely important when talking about the refraction of light, as to, for example, how lenses form images. We'll get to that, however, much later on. For now, this is, in terms of water waves, how we write Snell's Law. Okay, using this expression is very easy to do. When we do use the expression, it's usually nothing more than a little bit of plug and chug, and we do so in terms of degrees. So then therefore I have to switch my calculator back to degree mode to do the two example problems associated with the use of Snell's Law. All right, so at this point, go ahead and pause the film and then go ahead and access the first of the 2 lecture examples and copy it down into your notes. I'm going to do a little bit of erasing here and call that problem up onto my screen. Okay, now for the first of the 2 problems, I'm going to go ahead and use this diagram here once again. So if necessary, pause and then go ahead and recopy it into your notes. And then we have the following values. Okay, so plain water waves, are traveling at 3 meters per second in deep water. So in deep water, the V here is 3 meters per second, and the angle of incidence is given to us as a 30-degree angle. Okay, and then the waves slow down to 2 meters per second, so that's V prime, like so. And then what we're asked to find very simply is the value of the refracted angle. So I'm going to just go ahead and use Snell's Law, of course, in order to find the refracted angle. Let's go ahead and do some cross multiplying with Snell's Law and solve it for sine theta refracted. So take sine theta refracted and move it over here to the left-hand side, like so. And then cross multiply these things here to the right-hand side of the expression, like so. And then at this point, we do nothing more than just plug in the numbers and then solve for sine theta refracted, and then theta refracted from there. Okay, now when I do start to plug in my numbers, notice that V prime over V, 2 over 3, well, that's a number that is less than 1. This then means that the refracted angle is going to be less than the angle of incidence, and that's exactly, of course, what I drew on the diagram above. You do have to be familiar, by the way, with how to draw this diagram. It will be referenced on the next exam. Okay, now I have to switch my calculator back into degree mode here in order to do the problem. So what I have here is, first of all, 2/3 and then multiply by the sine of 30. And then take the inverse sine of that to get the refracted angle. Okay, and then when I do, the refracted angle here is about 19.5 degrees. So then therefore, as the waves approach the shore and slow down as they do, the refracted angle gets less and less. Eventually, just prior to breaking, it ends up basically being equal to 0 degrees. Okay, now there is a second problem. In the first example here, we just described what happens if the waves slow down, but they could just as easily speed up if the refraction is in the opposite manner. So go ahead and pause the film at this point and copy down the second problem into your notes. I'm going to do some erasing here, and then I'm going to adjust the diagram as well. Okay, so beginning here, go ahead and take a moment to copy this portion here of the diagram into your notes, and now we have the following. Okay, plain water waves are traveling at 3 meters per second in shallow waters. Now this here is shallow water, and the speed is 3 meters per second, and the incident angle is once again 30 degrees. But now the waves cross a boundary from shallow to deep water. Like so, and they have a new speed here, V prime, that's given to us as 3.5 meters per second. Once again, mathematically, there's nothing more than a little bit of plug and chug here in order to solve for the refracted angle. So before I complete the diagram here, let me go ahead and just use Snell's Law to find that refracted angle. So here's my cross multiplication from earlier. I'm just going to use it again, but first of all, take a look at the ratio here of speeds. This is 3.5 divided by 3. The ratio of speeds here is a number that is greater than 1. This then means that the refracted angle is going to be bigger than the incident angle. Let me now just go ahead and solve for it. I'm once again doing a little bit of plug and chug. All right, so the ratio of speeds here is 3.5 divided by 3 and then multiply by the sine of 30 degrees and then just take the inverse sine of all of that. And when I do the refracted angle here, I'll round it off a little bit, is about 36 degrees. So then how do I draw a bigger angle? The angle of refraction is greater than the angle of incidence on the diagram above. Well, if the waves speed up, this then means that the new wavelength has to be greater than the old wavelength. The lambda prime in my original derivation is now a bigger number than the original lambda. So how do I draw that on the diagram above? Yes, you do need to be familiar with how to draw this diagram. The refracted wave crests now have to look like this. I'm going to kind of exaggerate it here for clarity. Like so. Where right here is the new wavelength lambda prime, and notice that it's larger than the original wavelength lambda. Perpendicular to these wave crests is now the direction of propagation. Like so, where right here is a right angle. So notice that when the waves cross the boundary from shallow to deep water and speed up, they refract like this, in this direction, like so, as opposed to the first diagram when they slowed down and refracted like this. Right here on the diagram is the angle of refraction, and that angle there, the 36-degree angle, is greater than the angle of incidence. Yes, you do need to be familiar with how to draw both of these diagrams. They are the starting point later on for ultimately describing how light refracts to eventually form images. We'll get to that later. Okay, this concludes part 1 of today's lecture. Let me go ahead and pause.